Right, here we are in section 6.6. We're going to be talking about modeling real-world data using sinusoidal functions. We've talked before about sinusoidal functions. Basically, they're any function that can be described by a sine of x or a cosine of x function. And we know that we have two ways of writing out sine of x and cosine of x functions. Well, the textbook does one way, I do this way, and then unfortunately Desmos, which we're going to be using, does it a slightly different way, but it is a little bit more in line with the way that we have discussed as opposed to the way the textbook discusses. So if you're looking at the textbook, totally fine. Just realize that there's this slight situation where they don't factor out this term, where they would have it as bx minus c without the parentheses, therefore the b is already multiplying with the c. I hope that makes sense. We've talked about it before. Okay, so with that in mind, let's look at this first example. This example refers to the weather, not the weather, the amount of the sunrise and sunset in Brownsville, Texas. And basically what we see is that on the 15th of every month, the sunrise and sunset was measured, throughout an entire year. And that information is recorded here. What we're supposed to do is to find the difference between these two values, meaning the amount of hours of sunlight per installment or per bit of information. And then we're going to use that information to create a function, and we're going to then use that information to estimate the number of hours of daylight on September 30th this particular year. And so what you'll see in the text is not only a different equation, but you'll also see the use of a calculator. And at the writing of the textbook, that was like the best thing to use at the time. And so that's pretty cool. But if you don't have a calculator, and that's not something we've been pushing in our class, we are going to use Desmos. So I'm going to pop over to Desmos real quick and show you what I have cooked up. So what I did is I took the information, one being January 15th, and I put the sunrise time, it was 7:19. The sunset time was 6 o'clock, and then I just put it in here. And partly is because I wasn't paying attention to what I needed to do. When I realized that I was supposed to find the number of hours of daylight, then I came over here and said, oh, please calculator, subtract those two values for me. So the calculator did that. I had these other ones posted, like the dots or the values for the other ones, but since they're not pertinent, I erased those. And I was going to try to make another column here, so that instead of having two variables here, I had one, so the calculator would be comfortable, but I was having trouble with that. So I'm sharing all that with you just so you know that this was a bit of a hit and miss for me, but I'm still going to be able to show you how to do sinusoidal regression. So definitely pay attention, take notes if you must. So watch this. So basically, as I mentioned before, the equation is going to look very much like what we have been using, except just focus on the equation for a bit. I have y sub 2 minus y sub 1. Again, this should sort of just be like one variable, y, but I had to do that because the way I named the column. Stay with me, I hope that makes sense. Anytime you're doing regression in Desmos, you need to make sure you have the subscripts on the value, or the calculator will not know to go to the chart that you have created. Notice that this is not x, but x sub 1, and I had to use again y sub 2 minus y sub 1 because that is the name of this column. And then so I use not an equal sign, but the tilde. It's on your computer, probably near the number 1. And you're going to then put in this equation. So this is like the equation that I showed you, because the b term, they have it as k, kind of like the textbook, which is cool, is factored out, and then this d term is there, and it shows the phase shift. So here a is the amplitude, k deals with the period, it is the factored out term that I call b, d is the phase shift, which I have as c, but that's okay, it's still relevant here, and c is the vertical shift up and down, where I would call it d. Not a big deal, but just want you to understand. So now that you have that, you now have the equation that you need in order to figure out the actual fit that's happening here. So this information is given. So now I'm going to write up this equation by writing y is equal to, and instead of a, I'm going to put that 1.59 value, 5953. I'm just being a bit of a nerd by putting all the information in there. It's not that big a deal. Sine of, and so now I'm going to open my parentheses. The k value is 0.51247, and open another pair of parentheses, and then I have my x minus the d term. You guys see what I'm doing. I hope it makes a whole lot of sense. So what we're hoping to see when we're done this is that we get a really nice graph that's going to fit perfectly into the data that we have. And so the next thing I'm going to do is lift this up a bit by adding the c term, which is 12.1182. And we see we have a beautifully well-fitted graph for this situation. And so that's kind of pleasing. I don't know about you, but that feels right to me. And so now that we are dealing with trying to figure out that last bit of information, the last bit of information was to determine the value of the number of hours of sunlight possibly on September 30th. I'm going to look at September 30th is midway between October 15th and December and September 15th, and so that will be midway between 9 and 10. So I'm going to put a vertical line at 9.5, and so x is equal to 9.5. And when I do that, I get right to the place that I want, which is there's approximately 11.926 hours of sunlight on September 30th in Brownsville, Texas. All right, I hope that made sense. Go ahead and play around with Desmos, see what you can find out, share that information with me because I'm new to all the things on Desmos too. Even though I've been using it for a while, I'm still astonished at all the cool things that we can find. Okay, so for example 2, we are asked to create a function for this particular situation. So, and since we're dealing with sinusoidal functions, we can assume that that's what we need to do. So an average seated adult breathes in and out every 4 seconds. The average minimum amount of air in the lungs is 0.08 of a liter, and the average maximum amount of air in the lungs is 0.82 of a liter, or 0.82 liters. Suppose the lungs have a minimum amount of air at time t equals 0, where t is the time in seconds. So let's go ahead and do a really terrible drawing of what's happening. We've got our minimum amount. It doesn't make sense to go. So the minimum amount is down here. And so 0.08 liters, it doesn't make sense to be in negative amounts. That isn't sensible. And then so we're assuming that we breathe in, we get a maximum amount. Let's fix that. Breathe in, maximum amount, comes back down, comes back up, comes back down. So we're dealing with a curve that looks like this. And if you are thinking about like doing the easiest thing, because you know that it can be described, any of these functions can be described as a sine or cosine, it seems like a cosine would be easier. And the reason why is because cosine, we know, starts like this. Let me do a cosine real quick. Cosine, we know, starts up at the top and goes down and up and go down and up. And so the reason why I'm choosing cosine is because if we took the cosine function and flipped it, then we'd basically have this graph without having to have a phase shift left and right. Whereas if we thought about the sine function, which starts here and goes down and comes up, then we know that we would have to have a phase shift in addition to having all the other changes. So let's go ahead and describe this as a cosine function. So that means we've got y is equal to a times the cosine of b times x minus c plus d. And so we're going to avoid this part because of what we chose. So we won't have a phase shift. We'll just have the sine of bx. I don't really need the parentheses anymore either. So we'll just have this sine of this value here. Scooch this over here. And so this is what we're looking to figure out. So a couple things we need to do. We need to figure out what is the amplitude. And so we know the amplitude is going to be negative. right? Or the coefficient that's going to lead us to the amplitude is going to be negative because we're flipping that cosine function. But we also need to figure out what it is, and we're going to figure that out by finding the half the distance between those two values. So half the distance from the base to from the lowest value to the highest value is going to be 0.37. So we're going to start off with a negative 0.37, and then we've got the cosine of this value here. So we know that an average adult takes the breaths in and out every 4 seconds. So that's giving me the period. And if you remember, the period is equal to 2 pi divided by b. And if the period is 4, then 2 pi divided by b is going to be 4. And therefore, you're going to see, if we calculate this, b4 is equal to 2 pi. And then we're going to divide both sides by 4, and we're going to get pi over 2. So we get the cosine is going to be pi over 2 x plus d. Now this d value we're going to figure out by figuring out how high from, like, where the midline is. So again, knowing that we have the difference between these two is going to be like 0.74. Let me try to do this again. So the difference between these two is 0.74, and then when we cut that in half, we got 0.37, but we add that 0.37 onto the lowest value. Are you guys with me? I hope so. And we get 0.45. So we're going to be at 0.45 here. Let me go ahead and just change this d value to that. And so that's how we come up with the equation. Does this make sense, guys? I wish I could talk to you all and hear your voices. So let's kind of go back over what we did. We looked at it. We found that the amplitude was 37. We know we're going to do 0.37. We're going to do negative 0.37 because we're flipping the cosine function. We identified the period as 4 seconds, since we have that breathing in and out situation at 4 seconds. We use the period equaling 2 pi over that b term to get that b was equal to pi over 2, and that's the x value there, plus 0.45. And then so we're going to graph this function, and we're going to graph it not by hand, but we're going to use Desmos, and then we're going to determine the amount of air in the lungs at 5.5 seconds. So let's see if we can do that. So I've gotten to Desmos and I put that information in there, and here is our graph. Hopefully it looks good to you. It looks pretty good to me. And the next thing we're supposed to figure out is how much air a person has in their lungs at 4.5. Let's see, at 5.5. So we come over here. It's nicely labeled at 5.5 seconds. We have approximately 0.712 liters of air breathed in as an adult. All right, so with that, that's all we have. And I guess it's because these problems are somewhat time consuming to do by hand. Take your time, try your best with the work that we have, and let me know if there's anything I can help you with, because you gotta kind of work at these. They're not easy. Listen, take it easy. I look forward to talking to you guys soon. Bye bye.